All right, guys, we are on to chapter 2, 2.1 notes. So this in your notes packet, I believe, is page 50. And we're going to start talking about tangent lines and their slopes and what that means. And then we're going to talk about this cool thing called a derivative, which you've been waiting to hear forever. So it's kind of neat to know what is a derivative. You heard people talking about taking derivatives and differentiating and what's the derivative. So we're going to learn about that today. All right, so here we go. So we're starting with definition of a tangent line with a slope m. So what we've done in the past, like you can find, if I have a graph, right, any graph, you can find the slope of a line. Very easy, right? Rise over run, use your slope formula, change in y over change in x. We know how to find that. But what we're talking about now is what if I have some graph that has all these curves on it and has all those different things? How would I find its slope? Well, you can't find its slope anywhere because the slope is changing as it's different, right? But what you can find is if you go to a certain point, wherever you want to find a certain point, you can find the slope of what's called its tangent line. So I draw a tangent line at that point. Now, tangent means it just touches it once, right? So tangent line just means touches exactly one spot. Okay, so it touches it right here once. That's the tangent line. Now, if that's a line, I can find its slope. I can do rise over run. I can change in y over change in x. I find another point. I can figure that out. And then what we do is we make that difference really tiny. So we're trying to find that limit of that really tiny limit with another line here. Make it really small. And as that change in x gets smaller, we can actually estimate the slope of a curve. So this is the way to actually find the slope of a curve, is by taking the slopes of the tangent lines really close to that point, okay, and getting it really small. So this is the actual definition of a tangent line. So really it's the limit as change in x becomes 0, as delta x becomes 0. That's what that part means on the denominator there, right? On the denominator on the bottom. So we're looking at as that change in x becomes really small. That's why it's a limit. And then up here you see this is a difference quotient. And really what a difference quotient is this is slope is what this really is. Because this is the y value. This is like your y2 minus y1. Those are both y values. At the bottom, change in x, or that's just x2 minus x1. So this is just a fancy way to say slope. It's f of c plus delta x minus f of c all over delta x. Okay, so this is the long way to find the slope of a tangent line, and we are going to use it, and I'll show you there's another version of this formula that we'll see on the next page here, but let's practice with this idea first, okay? The slope of the tangent line is also just called the slope of the graph right there. Okay, so when we say the slope of a curve, we're not actually finding the slope of the curve, we're finding the slope of the tangent line to it, but sometimes we'll just call it the slope of the curve. So here, we want to find the slope of this graph at the point 2, 1. Now this is interesting. You guys look at that. That's a linear graph, 2x minus 3. What is the slope? Well, we all know that the slope is just 2, right? So obviously at the point 2, 1, right, this was my graph, looks like this. At this point, my slope is still just going to be 2, right, because that's what our slope was. So we know the slope is going to be 2, but let's use the formula and prove to you how would I use this formula and what should I do here, okay? So the way we're going to start with this is we're going to do our difference quotient just like you did on the last page. So you're going to first find f of 2 plus delta x, which means I have to take this whole quantity, 2 plus delta x, and plug it in for x. So it's going to give me 2. Instead of x, I put 2 plus delta x minus 3. Okay, then I'm doing the second part, minus over here, f of 2. Okay, well, what's f of 2? I just plug in a 2 all over delta x. So delta x here is a variable. And don't forget, we are taking the limit as delta x turns into 0, as delta x goes to 0. Delta x is a variable. It goes together. The delta and the x, they're together. Bien pegaditos. You don't separate them. You keep them together, okay? So what we do now is let's simplify this, and hopefully some stuff will cancel. I can distribute, work this guy out, minus it. So let's see, I'll get 4 plus 2 delta x minus 3. So what is this? 4 minus 3, which is just 1. So minus 1 all over delta x. Well, 4 minus 3 minus 1, boop, 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 that's just 0. And then I would have 2 delta x over delta x. The delta x's cancel, and I just get 2. So what's the limit? Don't forget there was this limit in front. As delta x approaches 0 of a constant 2, well, it's just 2, which we knew it was going to be because that was the original slope, right? So it does work. Obviously, you wouldn't use this for a linear graph, but you would definitely use it for one like example 2 that's not linear. So we're going to try and find the slopes of the tangent lines of this function. Let's just get an idea what's happening here. X squared plus 1 is our parabola that's gone up 1. And we want to find the slope at these 2 points. First at 0, 1. So at that point, I want to know what's the slope. And at the point negative 1, 2, I want to know what's the slope. Now really, we're technically talking about the slope of the tangent line there. So if you were to draw a tangent line here and draw a tangent line here, that's what we're trying to find. What are the slopes of those tangent lines there? Okay? So we're going to let c, f of c represent an arbitrary point. So this is our formula back from up here. Okay, limit is delta x approaches 0, f of c plus delta x minus f of c all over delta x. So let's just start with the equation x squared plus 1. So I'll now have the limit as delta x approaches 0. So I'm going to start with this, f of c plus delta x. So for x here, I'm plugging in c plus delta x squared plus 1 minus the whole thing, f of c all over delta x. All right, so now I got to work this out. This first part here, I have to actually FOIL that out, right? So I'll get c squared plus 2c delta x plus delta x squared. This minus distributes. All right. And on the bottom, we still have a delta, oh, whoops, I'm listening to Sam, like something seems wrong. That's what it was. This was f of c. Sorry, my bad. So this guy here and here should have both been c squared because it was f of c, so I had to plug in a c there. Okay, that looks better now. So now my c squareds cancel, my 1's cancel, and then I'm left with 2c delta x plus delta x squared all over delta x. So what I can do is in this numerator, I can factor out a delta x so that it cancels. And so now I'm just left with this, the limit as delta x approaches 0 of 2c plus delta x. Okay, so now we know how to do limits. We just did limits last year. For the entire past month, we didn't do limits, right? So, maybe not a month, but it feels like it. So you're going to take this 0. We're going to do direct substitution. Plug it in. So what do I get? I get 2c plus 0, which is just 2c. Okay, so what I call this is my slope generator. Okay, so what that does is it's going to generate the slope for me at any point c. All right, and that's for the x value. That's my x. Okay, so at any x point, x value of c, and I can pick any c's I want. Well, they already gave us some c's, right? Remember in this problem, they were trying to find at the point 0, 1 and negative 1, 2. So those are the c's that we're going to use. So let's see. I'll go over here. So for the point 0, 1, I'm going to plug in to this equation 2c. I'm going to plug in that the slope is going to equal 2 times 0. And so I just get 0. At the point negative 1, 2, the slope is 2. I'm just plugging in the x values here. So it's negative 1. Okay, so hopefully that kind of makes sense that I'm taking that x value and plugging it into my slope generator for c. And that's going to give me the slope. So if you will, right, this equation that I get here is just m. Okay, now let's think about this. Go back to that graph. Does it make sense that the slope was 0 here for that line? Totally, because it's horizontal. And the second one was negative 2. Does it make sense that this slope would have been negative 2 for that line? totally, because it's a downward negative slope. Okay, so it should make sense graphically as well as algebraically. All right, so sometimes like this part of working it all out is going to be kind of long. Okay, it's definitely the long way. So that's going to take a while, and you got to be really careful with variables like I did. I messed up there for a sec, and double checking your work, right? But that's what the answer keys are there for. All right, so a couple things here. Let's keep going, and then we'll get to derivative. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. Okay, for vertical tangent lines, you're either going to have infinity or negative infinity. As we talked about before, right? Anytime you've got those vertical asymptotes, that's when you're getting infinite limits, okay? So the vertical line would be if you got the infinity or negative infinity, that's when you're going to have a vertical tangent line. All right, so the moment you've all been waiting for now. Let's talk about this word. Dun, dun, dun. Derivative. There it is. All right, so definition of derivative. It says the derivative of f at x is given by, and then we've got this new notation here. You see that little apostrophe or that tick mark up there? That's called f prime, okay? F prime, and that's how we show a derivative. It's just a symbol that means derivative, but we read it f prime, or we can read it the derivative of f, okay? And we'll talk about some notation here in a sec. But that's the most common one. There's other ways, and I'll show about some other ones in a second. But what is the definition of derivative? All right, it's a limit as delta x approaches 0. Well, that looks pretty familiar. We just talked about that. Of f of x plus delta x minus f of x over delta x. This looks really similar. Didn't we just talk about that right here? Isn't that the same thing as that? Well, it's close to the same thing, except this one had c's, and this one has x's. So it's pretty much the exact same thing. But wait, what was that? Well, that was the definition for the slope of the tangent line. So if this is the derivative and it's the same as the slope, what is the derivative? You're right. The derivative is just the slope. Dun, dun, dun. Okay. Super crazy, right? That's all the derivative is. I know, it sounds like a very, very fancy word to sound super smart. You've actually been taking derivatives for your whole life of algebra as you've been finding slopes. You've really been finding the derivative. So the derivative is the slope. Now, the tricky thing is now we're going to be able to find slopes of curved lines, not just straight lines. So we're able to find the derivative of a curved line, which is why it's called a derivative now and not just slope anymore, because slope technically is just for straight lines. Okay, but this is what I want you to get in your heads, is that all that derivative is the slope. Okay, so this is the definition we're going to use. There is also an alternate definition that I use sometimes. So let me show you the alternate form. I'll get some space here. All right, so alternate form. And you can use either one as you're solving these problems, and you'll see sometimes I switch back and forth. The alternate form would be that the f prime of x, or the derivative, again, it's still the limit, but in this case it says x approaches a, or sometimes you'll see other variables, of f of x minus f of a over x minus a. You saw this one. This was those difference quotients, right? So this is that other difference quotient that you did on page 49, where you did all those difference quotients. So there's the first one over here, right? That was the first difference quotient. That's the delta x form. And this is the one with more of a traditional slope form. You can use either one. It'll work every time, okay, as we go through to find these new derivatives. Okay, so what I want you to recognize, a couple things. Derivative of a function is also a function, right? So that's why I called it the slope generator, because it's a function. So that for me is the derivative. Because it's going to change. There's not just one slope everywhere. The slope is going to be different at all these different points. So it's a function that will generate the slope at all these different points, if that makes sense, okay? The process of finding the derivative is called differentiation. The verb kind of changes there. So we'll talk about things being differentiable if you have a derivative. differentiable if it's differentiable on the whole point, if you can find a derivative on every point there. All right, here's some more of that notation that I talked about. So you might see like this with the little tick mark apostrophe, we read f prime of x. You can also say dy dx, that just means derivative of y in terms of x. Sometimes you'll see y prime, derivative of f of x in terms of x, or a capital D derivative of y in terms of x. And we say the derivative of y with respect to x. And again, here's just your formula, change in y over change in x, derivative, f prime, all that stuff means the same thing. Or again, you could use that alternate format that we talked about. Okay, let's try some, because now it's like, what just happened? All right, so let's put it into practice. Find the derivative of f of x equals x cubed plus 3x. Okay, so I'm going to write f prime, because that's the derivative, equals the limit. And I'll use the original definition. We won't use the alternate. As delta x approaches 0, I'm just going to write it out first. F of x plus delta x minus f of x all over delta x. You're going to get this memorized just because you're going to do it so many times. All right, so now let's work it out. I want f of x plus delta x. Whoops. So that's going to be, instead of x, I've got x plus delta x to the third plus 2 x plus delta x minus parentheses x cubed plus 2x, because that's the whole thing, right? So this is this first part here, f of x plus delta x, that's all this, right? And then this minus f of x is the green part there. Okay, now we're still all over delta x. All right, so this is where you got to work this out now. So you've got in this first part x plus delta x to the third. Eesh. But if you remember Pascal's triangle, this isn't too bad. So you can remember it's 1, 3, 3, 1. So it'd be 1 and then 3 x squared delta x, 3 x delta x squared, and then 1 delta x cubed. So if you remember Pascal's triangle, you can kind of work that one out pretty quickly. Otherwise, you'd have to FOIL it all out, and you'd get that same answer. This next part, I'm going to distribute the 2. And then here I'm going to distribute the negative and hope that some of this stuff cancels out. And let's see. So what canceled? My x cubes are gone. I had a 2x minus x is gone. All right. Now from all of that, I can definitely factor out a delta x on top, because they all have delta x's. And this is what I would be left with. And then my delta x's cancel. Now I can't forget, I was still taking the limit as delta x approaches 0. So now I'll do direct substitution into the remaining stuff. So if I plug in a 0 here and here, I'll just have 3x squared plus 2, because this whole thing will be 0 and that part would be 0. So this is my derivative function. And it is a function, right? That's the slope generator that will get me the slope of this graph. Now this is some cubic graph, right? It's x to the third. I don't know what it looks like. But now this function that we got as our answer here, that's going to generate the slope at any point that I choose along my original curve, right? I can now find the slope. That's what the derivative does, okay? I am showing you this the long way. This entire first section, 2.1, you're going to have to do the long way, and I know it's a pain, especially when we get to section 2.2 and I show you the short way. You're not going to like me anymore, because you're like, why did I have to do it the long way for so long? But I do need you to know this is using definition of derivative. That's what this method is. Okay, so we're using definition of derivative. And you could have to see that like on an AP test. It could say, by using the definition of derivative, find the derivative, and not using the shortcut that I'm going to teach you the next unit. So you do have to be able to do it in both ways, okay? You can't just do it in the one way, right? So you have to be able to do the long way as well as the short way. All right, let's practice. I have two more examples here that I'm going to walk you through. Find f prime of x for f of x equals square root of x. Then find the slope of the graph at those 2 points. Okay, how about I use the alternate form for this one? Because again, you can really pick either one. So I'll do the limit as x approaches a of f of x minus f of a over x minus a. All right, so let's see what that gives us. F of x is just square root of x. F of a is just square root of a over x minus a. Okay, now if I did direct substitution right now, I would have a problem because I would have to replace a with x, right? Replace x with a, sorry, and I would get a minus a, which would give me 0 in the denominator, which I can't do. So I have to simplify this somehow. Well, last unit, you guys remembered you did some tricks with rationalizing. So let's go ahead and rationalize this numerator and see if that's going to help us. And so when I FOIL this guy out on top, right, outers and inners like cancel out, I'll get x minus a. And on the bottom, I'll still have that x minus a, and I'll have the square root of x plus square root of a. Again, I'm still looking for the limit here. So now my x minus a's are gone, and I have 1 over that. So now when I do direct substitution, that's much better. And it gives me 1 over root a plus root a, which is 1 over 2 root a. And for these purposes, you can leave that in the denominator. You do not have to rationalize anymore. So what we're going to say here is that my derivative is 1 over, now I know I switched variables on you there. I know that's annoying. I went from a to x. Why? Because our derivative we want in terms of x. That's all. We just want that slope generator to really give us the answers in terms of x. And so that's why I switched this to an x. All right, so this is my slope generator. This is my derivative. I found f prime, okay? Find the slope of the graph at these 2 points now. Okay, so let's find it. So I'm going to go over here where I've got some space. So at 1, 1, the derivative at 1, right? I'm always plugging in x values. Is just, I plug in a 1. Well, that's just 1/2. And then let's talk about at 4, 2. Would be f prime of 4, excuse me. You're always plugging in the x value. 2 radical 4, which is 1/4. And then it also says to discuss the behavior of f at 0, 0. So what's happening at 0, 0? Well, when I plug in a 0, I get a 0 in the denominator, which means that my slope is undefined there, which means it has a vertical tangent line. Because if you think about it, what does it mean? It means the slope is undefined, and you only have a slope undefined with a vertical tangent line. I'm going to use some space down here to draw the graph of this. We were talking about the equation of radical x, right? So that equation starts at 0, 0, and goes like this, right? That's that graph. And so at the point 1, 1, it said that we had a slope of 1/2. That makes sense. At the point 4, 2, our slope was 1/4 because it was flatter. So that makes sense, right? It was 1/2, then 1/4. Well, what about at 0, 0? So right here at 0, 0, the graph is coming in. Let me see if I can kind of show you this. It's coming in, and then it's curving downward like this, meaning it's going to come in like this and curve, meaning that right here at 0, right at that point, it does indeed have a vertical tangent line. Okay, so it does curve around and has the idea that it's getting a vertical tangent line right there, which is why my slope is undefined. And so you would say no solution, undefined, something like that. Okay, last example. Find the derivative with respect to t for the function y equals 2 over t. Okay, so we're going to use, they asked us to use this one. So they just, again, changed variables. It's t this time instead of x. Not a big deal. You can still figure it out the same way. So let's start. We're going to do the limit as delta t approaches 0. So f of t plus delta t. For my equation up here, I have to plug in t plus delta t minus f of t, which is just 2 over t, and it's all over delta t. All right, so I have a complex fraction here that I need to simplify. So however you want to simplify it, I could do this 2t minus 2 times t plus delta t all over t plus delta t times t. And then I'm multiplying by the reciprocal of that. Okay, so again, using whatever method you want, I'm going to distribute delta t all over t plus delta t times delta t. The two t's are gone on the top, and then this delta t can be gone from that delta t there as well. So now I should be left with negative 2 over t plus delta t times t. But remember, we're taking the limit as delta t approaches 0. So I got to plug in a 0 here, do some direct substitution. So that just gives me t squared on the bottom. I kind of went through that fast, so take your time and make sure you get the same answer when you work on it on your own. So dy dt is negative 2 over t squared. That's my derivative. Now, why did I use that format? Because that's the format they put in the problem, right? I don't know. I could have said y prime. I could have said, right, a different one. But I used dy dt because that's what they said to use there, okay? And that's our derivative. So that's it, okay? In this case, it didn't actually ask us to find it at a point, so I didn't have to plug in any numbers. It just asked to find that function. All right, so you're going to practice a lot of this, finding these derivatives using either this definition or the alternate definition. You can kind of maybe get a feel for which one you like better. It's not that one is easier than the other. They're both pretty long, either way you look at it. Okay, a lot of simplifying. Use the notes, ask me questions.